Alright, now let's see the principle of operation of a transformer before we look at examples. Now, when an alternating EMF or AC voltage is applied to the terminal of a primary coil, like I told us, the alternating EMF is coming from the electrical stations, from the high tension electrical networks and masts and stuffs like that. So when that EMF or voltage, like I told us before, current brings about voltage. Current is the flow of charge, and once charge is flow, EMF is induced. According to Ohm's law, the rate of um the current passing through a metallic conductor is directly proportional to the applied potential difference or applied voltage. All right. So when current is released, the output of current is voltage. So when an alternating voltage is applied at the terminal of a primary coil, so every coil has terminal, the positive and the negative terminal. What happens? An alternating magnetic flux is produced in the iron core. Now, this iron core, this links or threads the secondary coil. What it means is that when that voltage is applied, the applied voltage at the terminals of the primary coil, an alternating magnetic flux. It is that magnetic flux, according to Faraday's law, that will lead to the induction of an EMF, the generation of an EMF in the secondary coil. Because when the current is released, a voltage is also released at the terminal of the primary coil. There is changes in the magnetic flux of the field, and once there is changes, a secondary voltage will be generated in the secondary coil. Now, this process is called mutual induction or mutual relationship between the primary coil and the secondary coil. So what is mutual inductance? It is defined as the flow of the induced current or the flow of the induced voltage from the primary coil to the secondary coil. The flow of induced voltage or the flow of induced alternating current or alternating voltage from the primary coil to the secondary coil. Now, quickly, this brings us to the formula. It says the induced EMF in the secondary coil depends on the EMF in the primary coil. I've told us this before. The induced EMF, there will no EMF will be induced in the secondary coil until it is first induced in the primary coil. So until it is first induced in the primary coil. Now, this brings us to the relationship between the ratio of turns in the secondary coil and the ratio of turns in the primary coil. So that brings us to the formula. Because of this relationship, this mutual inductance between the primary coil and the secondary coil, the conclusion we can get from this is that ES over EP equal to NS over NP. What does that mean? ES stands for ES stands for the secondary voltage or the secondary EMF. EP stands for the primary voltage or the primary EMF. So the ratio of the secondary voltage to the primary voltage is equal to the ratio of turns in the secondary coil to the ratio of turns in the primary coil. What does that tell you? It tells you that there is a direct relationship between the voltage in both coils and the number of turns in both coils. You see, so that is that relationship that states that the voltage in the secondary coil is directly proportional to the number of turns in the secondary coil, and the voltage in the primary coil is directly proportional to the number of turns in the primary coil. Is called the law of transformer or the law of transformation in a transformer. That is the law. The voltage, the ratio between the voltage of the secondary coil to the primary coil is directly proportional to the number of turns in the secondary coil to the number of turns in the primary coil. And that also that's the first formula we have there, 7.10. And the second one is now showing a relationship that if the voltage, the first one, the equation 7.10 is showing us a relationship between the voltage in both coils and the number of turns in both coils, while 7.11 is showing us a relationship between the current that not only the voltage and the number of turns can be related, the current also can be related, because voltage is equal to IR according to Ohm's law. So that's how we have I times E there. IS times ES equals to IP times EP. IS times ES equals to IP times EP. IS is the current in the secondary coil. ES, the voltage in the secondary coil. IP, the current in the primary coil. EP, the voltage in the primary coil. Now, why is this formula used? Equation 7.11, because we want to express that 7.10 relationship as a function of the power that will be generated when current and voltage passes. Don't forget that why they used I times E is because we know that power is equal to what? IV, current times voltage. That is why we have I times E. I is standing for the current, E is standing for the voltage, okay? For the secondary, by the right hand side, I and E again, I or I times V, and you want to put it, is standing for the primary. So if you express it in terms of ratio, you see that the ratio of the secondary voltage to the primary voltage is inversely proportional to their current. Can you see? It is inversely proportional to their current. That means the higher the voltage in any coil, the lower the current in that same coil. So if the voltage in the secondary coil is high, that means the current in the secondary coil will be low. And if the voltage in the primary coil is high, it means that the current in the primary coil will be low. Let's look at the statement. Hence, the current in the two coils are inversely proportional to the number of turns in the coil, which also are inversely proportional to the voltages. Only the number of turns in the coil are directly proportional to the voltages, which is in equation 7.10. But in equation 7.12, it is showing an inverse relationship. Now, to use a transformer to increase an applied voltage, that is, to make the ES, which is the voltage in the secondary coil, greater than the voltage in the primary coil, we find from equation 7.10 that NS must be greater than NP, correct? Why? Because there's a direct relationship between ES over EP and NS over NP. Now, such a transformer which increases or steps up, another name for step-up transformer is an increasing transformer, which increases or steps up the applied or primary voltage, is called a step-up transformer. I've explained that before. Now, however, we'll see that from equation 7.13, that when the number of turns in the secondary coil is greater than the number of turns in the primary coil, it means that the current in the secondary coil is less than the current in the primary coil. Why? Because there exists an inverse relationship between them, and this will give rise to a step-up transformer. A step-up transformer. Why? Now, the primary current is greater than the secondary current, but the number of turns in the primary coil is less than the number of turns in the secondary coil, and also the number of turns in the primary voltage is less than the voltage in the secondary voltage. The relationship between current and voltage in the transformer is inverse, but the relationship between number of turns and voltage is a direct relationship. Similarly, when the voltage in the primary coil is greater than the voltage in the secondary coil, it means that the current in the primary coil will be less than the current in the secondary coil, and this will give rise to a step-down transformer. It will give rise to a step-down transformer. So combining the three formulas in equation 7.13, we have ES over EP equal to NS over NP equal to IP. Can you see how when it changes now? IP over IS. So quickly, the ratio NS over NP is called the turns ratio. So you can be asked to calculate the turns ratio of a transformer. It is the number of turns in the secondary coil over the number of turns in the primary coil. And it is more than 1 for a step-up transformer, and less than 1 for a step-down transformer. So let's look at calculations and as we round up.